All right, let's talk about partial pressures and mole fractions. So partial pressures comes from John Dalton, who found that if you have a vessel that has a mixture of gases, then the sum of the pressures is the sum of the pressures of each gas if it was alone. So the idea is that you can add up the individual pressures of each gas to get the total pressure in the container. So I have gas A that by itself would have 1 atmosphere of pressure. I have gas B by itself would have 3 atmospheres of pressure. I slap them in the same container, and I have a total of 4 atmospheres of pressure. It's pretty straightforward. Related to this is the idea of a mole fraction. Now, the identity of the gas doesn't matter, but the mole fraction is that the total number of moles in a mixture of gases is the sum of the moles of the individual gases. So what gas it is does not matter. It's just how many molecules or atoms are there. So we write this similarly. N total is equal to N1 plus N2 plus N3. And then the mole fraction, which is chi, you probably just see it written as X, but it is a Greek letter chi. It doesn't really matter, is the mole fraction of A. So the mole fraction of A is the moles of A divided by the total number of moles, and it's a percentage in decimal form. So the sum of mole fractions will always equal 1. So if a flask has 0.15 moles of carbon dioxide, 0.67 moles of O2, and 0.82 moles of H2, what are the mole fractions of each component? So the total moles, you just add them all together, 1.64 moles. The mole fraction of carbon dioxide is the moles of carbon dioxide divided by the total moles. So 0.15 divided by 1.64 or 0.09. Same for O2, 0.67 divided by 1.64 or 0.41. And then H2, 0.82 divided by 1.64 or 0.50. You add them up, they add up to 1. That's pretty much it. Now, these mole fractions and partial pressures are related. Okay? So if you remember, pressure and moles are related, right? PV equals nRT. So partial pressure and mole fraction also play together. So we can think about the pressure, the PV equals nRT, we can think about it, the total pressure in a vessel is equal to volume times the total number of moles times R times T, and the partial pressure would be equal to the partial moles, or the number of moles of the partial pressure of A times volume would be equal to the number of moles of A times R times T, right? Because the identity of the gas doesn't matter. The gases mix, but they don't interact. So the relationship between total pressure, mole fraction, and partial pressure is that the partial pressure is equal to the total pressure times the mole fraction. And the mole fraction is equal to the partial pressure divided by the total pressure. So that's the relationship between that and partial pressure. And because of these relationships, partial pressures can be solved kind of in any order. So let's do an example, and I'll show you what I mean. So you've got a 1,250 milliliter flask. It's got 0.15 grams of carbon dioxide, 0.56 grams of argon, and 0.08 grams of hydrogen. If the flask is at 35, find the partial pressures and mole fractions of each gas as well as the total pressure in the flask. Okay, so generally speaking, the first place you're going to want to start is with the mole fractions, because the mole fractions, since I know the masses, I can find the moles, and I can find the mole fractions really easily. So let's start with that. So I've got 0.15 grams of carbon dioxide. That gives me 0.0034 moles of carbon dioxide. 0.56 grams of argon gives me 0.014 moles of argon. And 0.08 grams of hydrogen gives me 0.04 moles of hydrogen. Okay, so those are my moles. So I add those together to get my total number of moles, which is 0.0574 moles. So now I know the moles of each individual component and my total moles, so I can find the mole fractions. So the mole fraction of carbon dioxide is the moles of carbon divided by the total moles, or 0.059. For argon, same thing, 0.244. And hydrogen, same thing, 0.697. Cool. So there's my mole fractions. Finish that. Answer that. So let's move this down. All right. So next thing I want to know is the total pressure and the partial pressures. Now, I could solve PV equals nRT using each of these mole numbers, but the easier thing to do is to find the total pressure first. So I know the total moles, so I can plug the total moles in to solve for the total pressure. So 0.0574 moles times R times T divided by the volume, and you'll get 1.16 atmospheres. Okay, so I got my total pressure, and I got my mole fractions. So remember, the partial pressure is the total pressure times the mole fraction. So the partial pressure of CO2 is 1.16 times the mole fraction of CO2, so 0.0684 atmospheres. Partial pressure of argon, 1.16 atmospheres times the mole fraction of argon. And the partial pressure of hydrogen, 1.16 times the mole fraction of hydrogen. And if you add all those atmospheres together, it should come back to the total pressure. So it's a lot of really small problems. They're not super complex, but it's a lot of really small problems. And you could go, and depending on how you approach it, you can kind of go in any order, because again, they're all interconnected. So you use one to find the other one, and you can kind of do it in the order you want to. All right, practice. 4 grams of nitrogen, 3 grams of oxygen, 2.7 grams of neon are placed in a 1500 ml flask at 37 degrees Celsius. Answer the following questions. What are the mole fractions? All right. So I've got 4 grams of N2. I've got 3 grams of O2. And I've got 2.7 grams of neon. Okay, so find the moles. So 0.143 moles of N2. 0.09375 moles of O2. And 0.134 moles of neon. So I add those up together. And you get 0.371 moles total. All right. So the mole fraction of N2 is going to be 0.143 over 0.371, or 0.385. Mole fraction of O2 is going to be 0.09375 over 0.371, or 0.253. And the mole fraction of neon is going to be 0.361 over 0.134 over 0.371, which is 0.361. So those are your mole fractions. Cool. So then the question is, what is the total pressure? Well, remember, our total number of moles is 0.371. So pressure is nRT over P, over V. So it's 0.371 moles times 0.08206 liters atmospheres per mole Kelvin times 37 degrees Celsius, so plus 273. You get 310 Kelvin divided by 1.5 liters, and you get 6.29 atmospheres. Final question, what are the partial pressures? Again, partial pressure is going to be equal to 6.29 atmospheres times 0.385. Partial pressure of O2 is going to be 6.29 atmospheres times 0.253. And partial pressure of neon is going to be 6.29 atmospheres times 0.361. So you just multiply the mole fraction times the total pressure, and you get the partial pressure. So for neon, it's 2.42. For oxygen, it's 1.59. And for neon, it's 2.27. So again, you can do that kind of in any order. The way I like to do it, generally this is the way the problem is presented to you, is do mole fractions first, then total pressure, and then it's really easy to get partial pressures.